Hi everybody, Mrs. Pesic here. We are looking at chapter 12, circles. And the first section in this chapter is 12.1, lines that intersect circles. So your goals in this section are to identify tangents, secants, and chords, and to use properties of tangents to solve problems. So let's talk about, first of all, the points that are associated with the circle. Of course, you've got points that are on the circle itself, like maybe this point right here would be on the circle, or this point, but then we also have points that would be considered in the interior of the circle, like those points are all in the interior of a circle. And then, of course, we would have points that are out here, like these would be the exterior points of a circle, so all the points that are on the outside of the circle. So then we have a few more terms that we should talk about. So these are all lines or segments that intersect a circle. So our first one, the definition is for a chord. A chord is a segment whose endpoints lie on the circle. So for example, segment AB is this segment right here, and it has its endpoints that lie right on the circle. So that's a chord. A secant is a line that intersects a circle at 2 points. So this is a line right here. This line intersects the circle in 2 points. So we would say, hey, line L is a secant. And then we have a tangent line. Tangent line is a line that's in the same plane as a circle and intersects it at exactly 1 point. So this line M here is a tangent line because it only intersects the circle at that 1 point, point C. So the point where the tangent and the circle intersect is called the point of tangency. So point C in this diagram is the point of tangency. So let's take a look at this example. We're going to identify each line or segment that intersects circle A. So, and of course, when we say circle A, we mean a circle with point A as its center. So in this case, can you name a chord in this circle? Well, I think I would name a chord like segment BC, right, with a little segment bar over the top. So that's segment BC. That would be 1. And then trying to get that to be a C. All right, that's segment BC. But I think we also could list segment EF as a chord, not the line EF, but the segment EF. If we're going to talk about the line, the whole line EF, then that's going to be something else that we'll talk about in just a minute. But if I only go from point E to point F, and that's a line segment, then that is a chord. All right. A tangent would be a line, so I need to have a line symbol. So a tangent line would be, looks like to me, I would say that's line L. Right here. I can't name it any other way because they didn't really give us another point on here unless I draw in my own point, but I'll say line L is a tangent line. That's supposed to look like a little script L there. How about a radii? Well, a radii would be, the radii is the plural of radius. So do you see a radius in this diagram? Well, I think I would say I can see a radius right here from point A to point B. That would be a radius. So I'm going to list that, segment AB as a radius. But I could also list segment AC as a radius. So segment AC is another radius. So taken together, these would be radii of the circle. How about a secant? Well, remember, a secant is a line. So if I want a line that goes through 2 or more points, well, then I would say maybe talk about line EF. Right, so there's line EF. I need the line symbol over the top. Okay, so that's line EF. And how about a diameter? Well, a diameter is actually a chord that goes through the center of the circle. So I think we could say that segment BC is a diameter because it's a chord that goes through the center of the circle. All right, let's take a look at this example. We're looking for again, we're naming some things. So if we're going to name a chord here, I would probably name chord QR right there. And again, I'm going to use the segment bar over the top. That's a chord. And I could say that segment ST is a chord as well. Segment ST. And how about a secant? Well, a secant, I would then say, how about line ST? Because a secant is a line. So if I say line ST with a line symbol over the top, that's going to be a secant. It's a line that goes through a circle in more than one, well, in 2 points, I should say. All right, how about a tangent of the circle? Well, for that one, I would name this line down here because it's only touching the circle at one point, namely point U, but I'm going to name that tangent of the circle line UV. All right, how about the point of tangency? We just talked about that. That point of tangency is going to be this point U right here. So I'll say point U is that point of tangency. And if I had to name a radius for this circle, I would probably say, how about segment SP? That's going to be a radius. And how about segment PT? Okay. All right, so that's another radius of the circle. And if I was going to name a diameter, I would say segment ST. Again, I'm talking about a segment and not the whole thing. So not the lines, just from point S to point T as my diameter. All right, so that brings up some more terms. We can talk about two circles being congruent if and only if they have congruent radii. So for example, circle A is going to be congruent to circle B if segment AC, that's a radius of this circle, is congruent to segment BD. All right, so that is going from, hey, the circles are congruent if the radii are congruent. And then we have the other one that says that segment AC is going to be congruent to segment BD, but only if the circles are congruent. So if you know you have two congruent circles, then the radius of one circle is going to be congruent to the radius of the other. All right, how about concentric circles? So the word concentric would mean circles that lie in the same plane, they're coplanar, but they have the same center. So the two circles drawn here would be examples of concentric circles because they have that same center point. All right, and then we can also talk about two coplanar circles that intersect at exactly one point are called tangent circles. So these two circles drawn in this diagram here are concentric, I'm sorry, they're not concentric, they've got a different center, but they are called tangent circles because they have, they do intersect at the same point, at exactly one point. And so those would actually be internally tangent circles because their centers are both within like that inner circle or both within the outer circle. And then the externally tangent circles, these circles also have one point in common, but that would be considered an external tangent. Okay, so let's find the length of each radius here in this circle and then identify the point of tangency and write the equation of the tangent line at this point. So I think if we're talking about circle, let's start with circle B. I'm going to start with circle B, then I can see that that has a radius of 2. So I'm going to say the radius is equal to 2. But for circle A, for example, that circle has a radius, I'll draw it out this way, has a radius of 4. So circle A has a radius of 4. And we're supposed to identify the point of tangency. So I would say the point of tangency is this ordered ordered pair, or this point right here, which has an ordered pair, it looks like a 3, 0. So this is my point of tangency, point of tangency. And I would say that's the ordered pair 3, 0. And then if I want the equation of the tangent line, equation of tangent line, that's going to be this line here, and that line, I can't just say 3, it's got to be an equation, and it's going to be the line x equals 3, because all vertical lines are of the form x equals a number. Okay, so we were talking about tangent lines, so we can talk about a common tangent is going to be a line that is tangent to two circles. So in this diagram, line L and M are common external tangents to circle A and B. And in this picture here, line P and Q are common internal tangents to circle A and B. All right, now let's look at these theorems. This first one says, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So the line tangent to a circle implies that the line is perpendicular to the radius. So in this sketch here, we have the fact that we have this circle with a line L that's tangent to it, and if line L is tangent to the circle, then that radius drawn to that tangent line is going to be perpendicular. So we're going to have a right angle there. And if you know, for example, that you have a right angle, get rid of that, get rid of that. Get rid of that. So if you know that you have a radius out to a line that's touching the circle, then you know that that circle, that radius is perpendicular to that line, and that line M is going to be tangent to the circle. All right. So armed with that good information, let's take a look at some of these examples. So here we have circle B, and then it's 9 units from point B to line EN. All right, and I can see that's 9 units, and they're telling us that from E to N is 12 units, and we're supposed to be finding the distance from point B to point N. So in this case, I think our best idea here might be to actually draw in that segment BN. And because of our theorem that says that a radius drawn to a tangent line is going to be perpendicular, that means we do have a right triangle here. So BEN is a right triangle. And so in this case, we can set up the Pythagorean theorem and say 9 squared plus 12 squared is equal to, I'll call this x, is equal to x squared. So we get 81 plus 144 is equal to x squared, and x squared then is equal to what? Let me grab my calculator. Okay, so I get x squared is equal to 225, and then when I take the square root of both sides, I get that x, that's the length of segment BN, is the square root of 225, which is 15. So I know that this length x here is going to be 15 units. And then for a little bonus question, let's try this one. What is the measure of angle NBE? So if I want the measure of angle NBE, that's this angle right here. That's going to require us to do a little bit of trig. And for example, I could take the opposite side from that angle is 12, and the adjacent side is 9, and that would be the tangent. So the tangent of angle B is equal to opposite over adjacent, so that's 12 over 9. And I can find angle B by doing tangent inverse of 12 over 9, as we learned in, the previous chapter. And so in this case, if I do tangent inverse on my calculator, tangent inverse of 12 over 9, that gives me, I'm working this out on my calculator right now, as I hope you are, and that gives me, I think, about 53 degrees. So angle B is about 53 degrees. All right, so let's take a look at this theorem. This one says if two segments are tangent to a circle from the same external point, then the segments are congruent. So if, for example, we have segment AB and segment AC, and they're both tangent to circle P, then we know that the two segments AB and AC are going to be congruent. So let's test out that theorem here. So if we're trying to find the length of y, trying to find y, so we know that this segment DE is a tangent line, and we can see that DF is a tangent line. So these two segments have to be congruent. So let's set 5y minus 28 equal to 3y, and we just need to solve this equation. So I'm going to subtract 3y from both sides, and I'm going to add 28 to both sides. So to me, it looks like I get 2y equals 28. Divide both sides by 2, and I get y equals 14. All right, one last example, and that's this one. Again, I see that I've got a tangent segment, GH, and another tangent segment, HK. That means they've got to be congruent. So I can set those two segment lengths equal to each other. I get 4 plus 2a is equal to 5a minus 32. And let's solve this equation probably by subtracting 2a from both sides and adding 32 to both sides. So I think I get a 36 equals a 3a. And then if I divide both sides by 3, I end up getting a equals 12. All right, and we could always plug in 12 to see if that works. Here I get 4 plus 2 times 12. That's going to be 24 plus 4 is 28. And then over here, if I get 5 times 12 minus 32, 5 times 12 is 60, and 60 minus 32 is also 28. So I think a equals 12 looks good. All right, and that's it for this lesson. Thanks for watching.